Hi, my name is Shahnawaz. In this lecture, we are going to study the continuous functions between topological spaces. But before that, let us recall what we did in the last lecture. So in last lecture, we were studying the neighborhood system. I mean, if we have a topological space, say xt, and suppose we are given A to be a subset of X, then we say this A is a neighborhood. Say A is any point in A, then we say A is a neighborhood of A if so A is neighborhood of this little a if there exists some open set of X. I mean, there is some u in T such that this X is in A and this A is contained in U. Sorry, this is other way around. I mean, this X is in U and U is itself contained in A. Then we say this A is a neighborhood of this little x, and this x is called the interior point of I mean X. So this is a little definition. So if xt is a topological space and this A is in A, sorry, and A is any subset of X, then A is said to be a neighborhood of A of a point A in A if there exists an open set I mean a set U in T such that this A is in U and U is itself contained in A, then we call A to be a neighborhood of A. This point, the point A is called the interior point of A. The point A is called the interior point of A. So if we look at the interval, say open interval AB, and suppose we are given a topological space R with the usual topology, then this AB is a subset of R, and then R is this open interval AB is neighborhood of each of its points, because to prove this, say we are given a point C in the interval AB. This means A is less than X is less than B. So we can find an open set, because R being a space equipped with the usual topology, then the open intervals, the basic open sets in R are the open intervals. So we can always find, so if we take the minimum, so this is A here, this is B here, this is, say suppose this is X here. Let us take say let us take epsilon to be the minimum of X minus A and B minus X. Then we can find, so then we have an open set, I mean the x minus epsilon and x plus epsilon, which is like this. So in this case this is the minimum distance, so we have this interval over here. This is x minus epsilon, this is x plus epsilon. So this is in tu with the condition that this x is in this open set and is itself contained in the open interval. So that means this open interval, this x was chosen arbitrarily. This means this open interval is neighborhood of each of its points. In other words, every point of an open interval is its interior point. Now we denote the set of interior pointers, so this is the notation. So the set of interior pointers of A is denoted by this A superscript a small circle, or sometimes by int of A. Now we have a small result here, a proposition which is a trivial one, that is the interior of a set A is the union of open subsets of A. I mean so let us write this way: let X T be a topological space and say A is a subset of X. Then we had the following. So we had the first item, A interior is the set of all open subsets of A itself. I mean A interior, suppose A has 10 open subsets, then A interior is the union of those subsets. I mean A interior is the union of all open sets which are sitting in A, which are lying in A. Second one is A interior is open. Third one is A interior is the largest open subset contained in A. So these are the trivial exercises. So if we prove the first, I mean we have to prove A interior is a set of all open subsets, not the set is the union of, is the union of all open subsets of A. So suppose so let U alpha, where alpha is in some index at J, be the collection of open subsets of A. Then what we have to prove? Then we have to prove this A interior is actually the union of all open subsets in A. So let us suppose this is U alpha here. So this is obviously this is a trivial one, because if we take, so let now to prove this, what we first show, we will first show that this is contained there and this is contained there. So for the first inclusion, so let x be any point in the interior. So that means x is the interior point of A, then by definition A is a neighborhood of x. So then there exists an open set U of x such that this x is in the open set U and is contained in the A itself. So this is true for any x. Now this x being in U and U being an open subset of A, so this would imply that this x is in the union, because this is the union of all open subsets contained in A, and here this U is an open subset which is contained in A. So this is the trivial one. Now for the reverse containment, what we are going to prove, we are going to take an element here and we are going to prove this reverse containment. So this is left as an assignment for the readers to prove the reverse containment. So this is trivial one. So actually this is easy, because this is true for any x in A interior. That means if we pick, so if this is A interior and if we pick any x here, for this x we have an open subset U here which is lying in there. So this means this A interior is actually, so this follows directly from the definition. Now for the second definition, this I mean for the second item here, A interior is open, follows from the definition of follows from first, because this A interior is actually the union of all open subsets contained in A. Since we know that the arbitrary union of open subsets is open, this would imply this A interior is open. Now for the third item, to prove A interior is the largest open subset contained in A, it also follows from the first item, because the all open subsets of A is given by this class here. So if we take the union of these subsets, this will be the largest subset in the open subset contained in A, and by definition it is over A interior. That means A interior will be over the largest subset of open subset of A. Now let us move towards the continuous functions. So this is the definition. So let xt1 say xt and yt prime be two topological spaces. So we call a function f from the set x to y a continuous function. If for any open subset, v of y means v is in t prime, the inverse image, the inverse image of this set V, this must be an open subset of X. i.e. this inverse image should lie in T. Then we call f to be a continuous function. Now continuity of a function does not only depend upon the function f itself, but also on the topologies specified for its domain as well as its range. So now, in order to check whether a function is continuous or not, I think we should not check this condition for any open subset here. We don't have to look the inverse image of each and every subset of T prime. Instead, what we do, we just look for the basic open elements of T prime, and we see whether the inverse image of the basic elements of T prime are open here or not. So let us make this remark. So let us suppose f is a function between, so let B prime be the basis for this for the topology T prime on Y. So we take a basis for T prime here, which is for B prime. So then, to prove continuity of f, it suffices to prove the inverse image of every basic element in B prime is open in X. So then, to prove continuity of f, it suffices to show that inverse image of every basic inverse image of every basic element B in this B prime, in this fancy B prime, is open in X. Now, why this is true? So the definition of the continuity is that, so if this is set X and this is set Y, and we have a function f here, and we have an open set V here with respect to topology T prime, then we call f a continuous function if inverse image of any open set here is open. If f inverse V is also open here. Now what we claim here? We claim here that we need not look this condition for each and every open set here. Instead, what we do, we just look at the inverse image of basic open sets. So if the inverse image of basic open sets is open here, then f is continuous. So if we take any open set in Y, so V is in T2, then this V can be expressed as union of basic elements by definition of the basis. So this is B alpha, where alpha is in some index set J. So now to prove, now let us look at the inverse image of V, which is the inverse image of this union here, which is union of inverse image of B alphas, where alpha is in J. Now if each f inverse B alpha is open, then we know that the arbitrary union of open sets is open, then this is open. So this V, F inverse V will be open if inverse image of each basic element will be open. So F inverse V is open if and only if F inverse B alpha is open for each alpha. Now, so this was the case when we are given a basis. So this is true, also true if we are given a sub basis. I mean, to check whether a function is continuous or not, we only need to check whether the inverse image of sub basic elements are open or not. So let us make this remark too. So suppose this is our remark first. So if say this fancy S prime is a sub basis for the topology T prime on Y, then to prove F is continuous, it will even suffice to prove that the inverse image of every sub-basis element in S prime is open in X. So then it will even suffice to prove that the inverse image of every sub-basis element in this fancy S prime is open in X. The reason for this, so since the arbitrary basis element B in this B prime in this fancy B prime can be written as the finite intersection of sub-basis elements. So this can be written as the finite intersection of sub-basis elements say S1 through Sn. That is, we can write this B prime as the intersection of these finite sub-basis elements. Then if we look at the inverse image of B prime, that will be the finite intersection where I runs from 1 to n F inverse of Si. So this F inverse B prime will be open if each F inverse Si is open. So if each F inverse Si is open, then F inverse B prime will be open. So if F inverse B prime will be open, then each F inverse B alpha is open, because the sub-basic inverse image of sub-basic elements is open. So this would imply the inverse image of the basic element is open. So if inverse image of each basic element is open, then inverse image of this V is open. Now there is a lemma which states two equivalent conditions for f to be a continuous function. So let f be a function between two topological spaces, say xt and yt prime. Then we say that, so then the following are equivalent. So first item is for any open set u of y, i.e. for any open set v in T prime, the inverse image of V is in T. So this means if every inverse image of V, if we take any open set here and take its inverse image, if it happens to be open here, then f is continuous. Or this is same as to say that for any a in X and each V in T prime with f of a in V, there exists a in X, there exists a open set in X such that a is in this open set and this image of u is contained in V. So we are going to first assume that inverse image of every open set is open here. We are going to assume f is continuous. So proof. So first implies second. We are going to assume the inverse image of every open set is open in X. So we have to prove second then. So that means for given a in X with this hypothesis, we have to prove this expression. So we are going to pick an element in X. So let a is any element in X and V be an open set which contain this element, which contain this image. So since this V is open in Y, so by our hypothesis, as we have assumed that first is true, so the inverse image of V is going to be open in here. So then by hypothesis, the inverse image of V is open in X, i.e. it is in T. Now this inverse image being an open set, we put it to be equal to U. So put U to be the inverse image of V. So now note here that this, so we are given X here and this is over Y here, and we have an open set V here such that f of a is in V. So if we are going to take its inverse image here, which is U, so this U is actually f inverse V. So that means this A is there, because by definition f inverse V is the set of all elements in X whose image is in V. So if f of A is there, then A is in this pre-image. Now note here, so this means, so this implies A is in U and f of U is contained in f of V. So one should note here, so this is V here, this is U here, which is f inverse V. So if we look at f of U, which is same as f of f inverse V, so this is going to be a subset of V, not equal to V, because if our f is not onto, so suppose this f is non surjective, so that means there is some part here which does not have pre-image. So if we take f inverse V, that means we are looking for the inverse image of this set, but f not being surjective means there is some portion of this set which does not have pre-image. So f inverse V means that only these elements in this portion has pre-image. So this U is, so this f of U is actually this portion. So that is why f of U will be contained in V, because f may not be surjective. In case f is surjective, then this inclusion is actually the equality, and so this implies A is in U and f of U is contained in f of V. So this containment may not be proper. So that is what we wish to prove. That means what we did here, so we take an element here and an open set which contain the image of this element, then we wish to prove this thing, i.e. there exists an open set U in X which contain this element A and whose image is contained in V. So we proved here for this element A, I mean for this open set V which contain the image of V, we have an open set U which contain A and whose image is contained in V. Now let us suppose the second is true and assume and prove the first item. So what we have to prove? We have to prove inverse image of every open set in Y is open in X. So we are going to pick an open set in Y. So let V be in T prime. So what we have to prove? We have to prove f inverse V is in open in X, i.e. it is in T. So there are two conditions. If f inverse V is empty, so there may be the case the inverse image of V is empty. This is empty. Then empty set being an open in X, so in this case the result is trivial. So then clearly f inverse V is in T, since the empty set is in T. So we are done in this case. Now assume this is non-empty. Let us first erase this. Now suppose f inverse of V is non-empty, and let A be any element in this set. So if A is in f inverse V, that means f of A is in V. So then f of A is in V. Now note that V is open set. Now there is this property that an open set is A is open if and only if it is interior is equal to A. So we call A to be an open set if A is same as it is interior. In other words, an open set is neighborhood of each of its pointers. So we have an open set V here, and there is some point f of A in V. That means this V is a neighborhood of f of A, because V is open and A interior is A. V interior is V, which means V is a neighborhood of any of its points. So this means V is neighborhood of f of A. So if this is the case, then there is some open set which contain f of A and is contained in V. So and hence there exists an open set or we are going to use our hypothesis here. So what is our hypothesis here? So we have to assume second, and we have to prove first. So this V is open here, and we have a point, we have this thing over here. So this V contains f of A. Now we have assumed the second is true, item second is true. That means if this is the case, then we have an open set U in T such that this thing is true. So then there exists an open set U in T such that U contains A and f of U is contained in V. Now that means V is a neighborhood of so if this is the case, this would imply, so this means, so f of U being a subset of V means, so this implies U is contained in f inverse V. So what we proved here, we proved, so f inverse is actually a subset of X. So this is our f inverse V. We chose an arbitrary point here A, and for this point A we proved that there is a subset, an open set U, which contains this A, and this U is contained in f inverse of A. So this means f inverse V is a neighborhood of A. This is the definition of neighborhood. So if we pick any element A here, and for this element we prove there is some open set U which contain A and is contained in F inverse V, that means F inverse V is a neighborhood of this point A. But this A was chosen arbitrarily, that means F inverse V is neighborhood of each of its points. So this means hence F inverse V is a neighborhood of each of its points. So F inverse V interior is F inverse V itself, but we know that F inverse V interior of a set is open. So this is done here. A interior is open, so this means F inverse V interior is open, and hence F inverse V is open. So hence F inverse V is open in X, which means that F inverse V is in T. Now let us do some examples of continuous functions. So let us take X to be a space equipped with the discrete topology, and Y with any topology. So B two topologies. Then so note that this D is discrete topology. So then any function f from x to y is continuous, because so this is set x here, this is set y here. So if we pick any, so if we prove an inverse image of any open set in y is open in x, then we are done. So let us pick an open set, say V in y, and let us look at its inverse image, that will be F inverse V, which will be a subset of x. But x is equipped with the discrete topology, and that means any subset of x is an open subset. So F inverse V being a subset of x, hence it is an open subset. So this means this is a continuous function. So let us do one more example. So let us take R equipped with the lower limit topology and the same set with the usual topology. Then again so then the identity function from R to R is continuous, because so this is over R, which is equipped with the lower limit topology, and this is over R, which is equipped with the usual topology. Now we have to prove the identity function is continuous. Now by identity function we mean which maps any element to itself. So if we take any open set, let us pick a basic open set, which in this case is an open interval AB, and let us look at the inverse image of this open interval under this map. So this is going to be an open interval. Now this map will be continuous if this is open, since we know that TU is contained in TL, I mean any open set with respect to usual topology is open with respect to lower limit topology. So that means this is going to be an open set in RL, because this TL is finer than TU. So in this case this will be a continuous function. However, if we look at the space, I mean the same function, but if we interchange the topologies, I mean we go from usual topology to lower limit topology, then the map, which in this case is identity function, is not continuous, because if we look at the inverse image of open interval here, I mean we have RU here, we have RL here. So if we look at a basic open set in RL, which is a semi-open interval, say AB, then this is open here. So under a continuous map, which is under the identity map, it is inverse image will be AB, and this AB is not open here. This AB is I mean not open, and as it is also not closed in RU. So we are able to exhibit an element in RL whose inverse image is not open here. So this identity map in this case is not continuous.